It's lovely. So I'd like to welcome you all to the Young Scientist session this afternoon. For those of you that don't know me, my name is Angie Lockwood. I'm part of RAFT Solutions here with Jonathan, and I'm going to be chairing the meeting this afternoon. Depending on time, we are going to keep quite tight to time this afternoon. If there's time for questions at the end of presentations, that's fine. If not, Agata's set up a shared document that she's going to circulate. So if you do have any questions and there isn't time this afternoon, if you'd just like to enter them onto that shared document with your name, and then we'll make sure that those questions are answered. Okay, so I'd just like to ask Ines and Gerbrich to join us for the first presentation. They're going to be presenting on precision phenotyping of resilience on a large dairy cow milk yield data set and comparison of milk yield based resilience indicators across purebred and crossbred dairy cows. Can I ask you to join us?
Sorry.
Let's spray you both first. So that's already open.
So good afternoon, everybody. My name is Ines Adriaens, and together with Gerbrich, we're from Wageningen University. We'll kick off this Young Scientist session, and our first presentation will handle the precision phenotyping of resilience applied to dairy cattle across purebred breeds, different breeds. Oh, wait. Ah, it works. Thank you all for being here. Ines and I will tell you something about the resilience of dairy cattle, focusing on different breeds. And in work package number 3, resilience was defined as the ability of a cow to recalve and to live a long and healthy life. In this case, we will focus on the response of dairy cattle to environmental challenges to create proxies or indicators for resilience. And those environmental challenges can really be anything like changes in feed or feed quality, weather extremes or pathogens. And this is already very relevant, but might become even more relevant in the future. As at least in the Netherlands, but I think across Europe, there is a transition going on towards more circular or nature inclusive dairy farming. And that might also imply that there is a large diversity in production systems, maybe adapted to local circumstances. And that's why different cattle breeds might come into place to serve different places in those different production systems. Well, measuring responses to environmental challenges can be done in different ways. In this time, we focus on measuring those responses in daily milk yield production because it's automatically collected and it's, well, very much available due to the automatic milking systems. And that has been done by previous researchers like Marieke Poppe, but also by Ines herself, because we know that disruptions or illnesses, heat stress leads to reduced milk yield production. And what Ines and Marieke both had in common in their research is that they focused on milk yield production, realized milk yield production, compared to an expected milk yield, so that you can really focus on the variability and also on the drops in the production. And that's what Ines will talk about a bit more now. There you go. Oh, yeah. Yeah, indeed. So my main part of the talk will be a little bit about the expected lactation curve and
what I want to do is just raise awareness of when we use data and real proxies for something that we want to phenotype and we want to apply on a very large data set, is how can we derive the information and what actually means the things that we derive from the data and the choices we make. So it's really about that. I implemented an iterated wood model. Marieke started from a quantile regression model. I will go a little bit into detail into both of them. But just to give you an overview, in the past, what we have been doing is really establishing a reference production for the quantification of these proxies, of these precision metrics that can be derived in an automated way. And very much apply that on purebred Holstein Friesian cows. And so the current research and the discussion of today, I hope, will go about what is the impact of the reference production that we do on the calculation of these proxies. And then in Gerbrich's part, how can we, or what happens if we quantify these resilience proxies across different breeds. So just to give a little bit of an overview of the data that we're working with, it's a pretty big data set. We start from first parity milk yield. First parity is always interesting because if you can derive whatever you want to measure from the first parity, you can make timely decisions for a second or a third calf. So you're pretty much in time. So we start from first parity milk yield, daily milk yield. And we had a data set available to start from 460,000 cows. Coming from a bit over 4,000 AMS farms, so really big data, but of course not. And I think yesterday we heard the same talk. So before you can start analyzing these data, you need to make a selection, make sure that the quality of your data are a little bit under control. So we looked for cutting off days in milk, but we had sufficient length of the lactation curve as well. But with gap sizes below 5 days and less than 5% missing data. So that are really the different criteria that we applied. And then we still ended up with 8 different breeds in the data set, and how the numbers that will Gerbrich will detail that a bit more. And then, so like I said before, we started from 2 types of expected milk yields. The first one is the quantile regression. What a quantile regression does is like you fit a 4th order polynomial, but instead of using all the data of your lactation curve, you make actually a weighting depending on where in your distribution you actually have the data available. So what you do is the higher parts of the lactation curve, so really the upper level, you give a higher weight than the lower level. And if you then apply that, you see that these kind of big perturbations do not really affect what you're estimating. So you really fit a curve through the highest part of this lactation. I did myself before. So in the past, you needed to throw away really the first part of lactation, because of course it starts from 0 or almost 0, but you can actually easily solve that by adjusting the weights in the beginning of lactation, just a detail. And furthermore, there are no further assumptions made on the shape of your lactation curve. So the only thing that you do is you fit it with a 4th order polynomial independent of the length of your data, and so on and so on. So this is a second example, a bit of a longer curve, so 305 days. The previous one was only 160 days. This one is 350 days. And again, you see very nicely that the curve is not really affected by this perturbations, but you also see that there is quite some flexibility in describing how this lactation curve look like. I don't know if you I can actually show it. If you look at how the average shape of a first lactation curve looks like, typically in a higher lactation, you have steeper increase and then a deeper slope. In this case, you typically have a little bit of a lower peak, but more persistent production over time, also because of the growth of the udder and biological development. And so if you look at the green line, this is really the average daily milk yield data with a 95 confidence interval, and the quantile regression curve and its 95 confidence interval really shows what you expect. It follows the line of the data in the upper part very well, but the lower part is actually not very well taken into account. So that's what you want to do. You want a reference measure. What if there are no perturbations available? And then one of the things that I want to show you is when you have really a deviating curve, like this one, you could expect that this curve would go up and something expecting like that it would stay around 30 or 25, going towards 25. Here, there seems to be something happening. And then you see this kind of S-shaped curve, which to me is very abnormal. But still, in this case, you see that the quantile regression follows this S-shape. It has the flexibility and the degrees of freedom to really fit this curve. And that is, of course, because you don't have model boundaries. You don't make any further assumptions on the shape of this lactation curve. If you then look at iterated Wood model, it's a procedure in which you fit a Wood model iteratively, where you will delete. Oh, fuck. This is can this be cutted from the YouTube video? Anyways, so this is actually the same curve as before, and you see that the Wood model also is really not affected by the big perturbation here, but it has quite strict assumptions on the shape of this curve. So you really have a 3-parameter model, nonlinear model as well, in which you can put some model boundaries to make sure that you remain this kind of shape. You can use the same kind of parameter structure to do the opposite, and then you have, for example, negative parameters and so on. So depending on what you know about biology and the expected curve, you can limit what you do. Same curve as I showed before. Here you see, oops. Here you see that this kind of shape, it is affected, so it doesn't really fit through this part very well, doesn't fit through this part very well. So it has to do with the kind of boundaries you put on the iterated part of it, where the quantile regression would really follow this shape. Here you see that it just gives a worse fit, but still allows you to calculate some of the residuals and the variability around it. So again, if you then look at how it looks like, so again, the real data is just fitted in the blue one, and then the red gives the iterated Wood model. You see again that it follows quite well the shape of the upper part, that it has a little bit less it follows a bit less on the data on the lower part. And here again, before the peak, still not perfect fit. So you need to take that into account in a way in your interpretation. And then if you look at a very deviating shape, yeah, Wood is just not able to fit this kind of things. And you see that it ends up, one of the parameters will become 0 or very, very small if you don't allow it to be 0, and you still have like a very bad fit. So in both cases, this is actually not a really real solution to say something about these kind of shapes. This is again a little bit of comparison with, because you don't have a real model boundary. So if you go look into the extremes, which is always very interesting if you do a model fitting on a very big data set, to look into the extremes to understand what the extremes are like. And so the extremes here show that by not restricting the model, you sometimes get an estimation that goes below 0, which is of course impossible. And in the quantile regression case, and here you also see that you have very deviating. So that's really a problem with a fitting procedure, where you get into a local minimum and not a convergence of the model actually. So what I wanted to show with this talk is that it's really important that you make the choices very conscious when you start interpreting the big data, and even though your data set is really large, it's still valuable to really look into how like things like the extremes, like visualize part of the data. Is what you're modeling, is it really what you expect to be modeling? By looking at your figures, making averages, looking at the extreme parameters, and so on. And we calculated the both models on the big data set that we had. And we saw that if we look into the features for resilience, that the correlation between these features are also not very high. So that means that however you decide to go on, and whatever decisions you make, and I don't say that you need to stand still, but you need to be conscious about the consequences of the decisions that you make. And it's really, so one of the things that I've also written down on the board is like, can we discuss this kind of quality control? Can we discuss these kind of pipelines for precision phenotyping and so on? So my message is try to visualize, know what you're doing, try to make the decisions consciously, and then move on and stick to those decisions. And I think that's a good moment.
Thank you. Yeah, so now it's time for me to show you some example of how this collection of daily milk yield and the residuals of that from the expected lactation curve can be used to compare different breeds in those traits. And I did that using the big data set that Ines already mentioned. And from that, we took all purebred animals. And this was a data set from the Netherlands. So there were quite a lot of Holstein Friesian cattle within that, 99%. But we also had some other breeds, which you can see here. So there were some local Dutch breeds like MRI and Friesian Dutch and de Groninger, but also some foreign species like Vlekvee and Jersey. And with that, we wanted to compare the different breeds. And yeah, we are aware of very different numbers of animals. Yeah, we have daily milk yields of all of them. I want to show you two different features that we calculated. And within these graphs, you can see in orange the daily milk production, and in gray the expected lactation curve, which is in this case the quantile polynomial regression, focused on 0.7. So in this case, as Ines explained, there's more weight on the higher numbers. And then so when you take the residuals from the daily milk yield of the expected lactation curve, you get a picture like this. And then we calculated the variance, which is the first feature, and also the autocorrelation. And well, the variance says something about the variability in milk production, and in this case, more about the variability under the lactation curve. And also the autocorrelation, which is expected to say something about the length of the drops and about the recovery time of the animals. Well, here we see a very stable cow. And then next to that, we see a cow that has a bit more variation. And we also see that in the indicators. Well, when we compare the different breeds, we first looked at the milk yield production. And as probably expected, the highest milk production was of the Holstein Friesians. And we saw that the Groninger, although it's a very small number of animals, was a lot lower. And also the Jerseys were a bit lower than the other breeds in the data set. Well, then looking at the variance, we see that the Holstein has the highest variance, suggesting that it's more variable in its milk production, as well as the Montbéliard is also quite high. And we see that the Groninger, the Dutch breed, is a bit lower than the others, as well as the Dutch Frisian and the the Frisian Dutch and the Jerseys. This is just the variance, but as I said, there's also a difference in milk production. So we made a linear correction for that, and we calculated the coefficient of variation. And then you see that there are some changes. So now the Holstein Friesian is not having the highest variation anymore compared to the level of milk production. But now the Groninger is a bit higher, as well as the Montbéliard is standing out, and the Jersey as well. So you see that within milk yield and variation, there is a connection. Well, and then we also looked at the autocorrelation. And here you can see it's quite comparable across breeds. We see that the Dutch Frisian and the Holstein are a bit higher than the others, suggesting that their drops and their recovery time are a bit longer. But yeah, it's not, the differences are not so big. So those were was an example of how we can use those features to compare different breeds. And I think based on the daily milk yield production and using an expected lactation curve really provides information about how animals, how their variability in milk production is, and that there is information in there about resilience. Well, we've seen that animals differ, or different breeds differ in their level of milk yields, but that there are also differences in variance and autocorrelation. So that suggests that different cattle breeds respond differently to environmental challenges. And yeah, we would like to explore this much further, Ines and I. And yeah, if you have any suggestions for future research, then we're very happy to hear that.
So we also thought a little bit about future research, and really think, like, we've already heard multiple times that we're dealing with a very complex trait, and that is very nice to look at what phenotyping decisions that we can make to actually characterize this trait and how these align with breeding priorities that we target, actually. And one of the things that we ourselves think of is, so we have the different features that have been calculated in the past, and so it might be interesting to not look at one or two, but really explore the use of multiple and combine the multiple features that are possibly calculated. And I think there is a little call for data of good quality, again, from different cattle breeds. Like Gerbrich already told us, like, we don't have a lot of data except for the Holsteins. So it would be really interesting and nice to take this one step further with a larger data set, and potentially also collect it in different environments. So we welcome discussion now.
Thank you.
That's lovely. Thank you very much. Can I just say, we've got 5 minutes. Has anybody got any questions they'd like to ask? And I'll wander over here.
That was really cool. Thanks. I was just wondering whether you can disentangle whether it's possible that some of those breeds might be more likely to be kept in more variable environments than other breeds, and whether you had any, I know this is really difficult to do because this is a problem I have with my data too, whether you can try and disentangle any of that. If you've got any ideas, I'd love to hear.
Yeah. Well, so I've been working with the data set that Marieke Poppe used. And I also worked with it within my master thesis. And there, yeah, if you have a large data set with just milk yield, then yeah, you can't say anything about the challenges and how big they are. And yeah, that. She has looked into the herd component in this, and she could find that there are differences between herds, and then so that there are herd differences, but also genetic differences within the animals. But more than that is not possible yet, I think.
And I just want to mention that we have it's Dutch farms within a automatic milking system. So I think if you compare like the variability for this compared to maybe what else of the variability there might be of the different production system that these breeds are kept, these are still already quite, or the most similar that we can get with an automatic milking system in the Netherlands.
Thanks for a nice presentation. You asked for some suggestions for future research, so I have one, I think. Have you considered exponential smoothing models? I think they could fit quite well for this type of data. So instead of, you could say, like you have the quantile regression model, this exponential smoothing, like the double smooth of Holtz.
I have explored a lot of possibilities. And at a certain point, I just went with one that I felt comfortable with, because I think that all of them and all the different possibilities have their own pros and cons and their own specifics. So it's one of the discussions that I want to open, is like, should we go for one commonality in there, or does everybody what they want, or how is the need in terms of breeding and in terms of precision phenotyping? But yeah, we explored a lot, but at a certain point you need to go with something.
Coming back to the first question, one basic assumption of your approach is that all breeds are facing the same challenges, and this, of course, with respect to environmental conditions, this might be true, but what if one breed is more susceptible to mastitis and the other more to claw problems, for example? Then you have different challenges and, of course, expect different reactions.
Yeah, that's a very good point. And yeah, that's also something that we want to explore further, using also more features than just these two, to see if there are differences between the breeds. And then, yeah, I think from other research and other studies, we know that there are specific differences. So I think it will be very interesting to compare which of the things that we know we can find back in these features, and to explore that a bit further. Yeah, because that's very valid. Yeah.
Oh, so really quickly.
Oh, okay, sorry, just a quick question. Did you use any machine learning and train your sort of model?
In a very broad sense, all the regression models that we do is machine learning. These are mainly model fitting procedures, so we don't do prediction models for the moment. So depending on what you mean with machine learning, it falls under it or not.
Fine, that's brilliant. Thank you both very much for that. Okay, can I ask Amir to join us for our second presentation, please? Okay, this is the evaluation of beef cow responses to feed restrictive challenges using a continuous piecewise linear model.
Hello, everybody. I'm Amir Aliakbari, and I'm doing my postdoc on work package 2.3 of the GINTER project. And I will present the evaluation of beef cow responses to feed restriction challenge using a continuous piecewise linear model. First, I will have an overview of the experimental design and the data. The experimental design started with 8 weeks of pre-challenge period with ad libitum diet, and then followed with the first challenge composed of 4 days of feed restriction that covered 50% of the animal's net energy requirements, and then 3 days of recovery with ad libitum diet. After 14 days of inter-challenge period with ad libitum diets, 3 successive challenge with the same composition were induced to the animals. And the experimental design was finished with 8 weeks of post-challenge period with ad libitum diet. This is actually not my slides. I updated them. Yeah. Well, anyway. We had in our all 3 batches, 22 Charolais cows from 3 batches. We had the daily measured dry matter intake over the entire experimental period. Milk yield measured by suckle, by weight suckle weight method. Plasma metabolism, including NIFA, urea, and beta hydroxybutyrate and others. And the daily data of the dry matter intake also, and I will explain later, with the average weekly. The initial objectives that we had decided for the, I really want to have my slides, thank you. Well, I informed, I updated the data before. Did you send them to It's back.
Is this one here?
Yes, exactly. Thank you. Thank you. That's fine. Yes, these are the right. Well, the initial objectives that we have defined, first assessing the resilience indicators, and we have focused on estimating change of response rates after a single nutritional challenge. And the second objective was to assess robustness indicators, and we have focused on estimating change of response rates after 3 successive challenges. The third main objective was to assess relationship between different clusters of animals based on these indicators with feed efficiency. And we will cluster animals based on indicators that were more informative and responded quickly to the imposed nutritional challenge. And after that, we will seek possible links between clusters and residual feed intake change. Well, the data changed, but here we had the residual feed intake data measured during the growth, early, and mild lactation of the animals. Following the objectives, we have first started with the repeated measures analysis to represent overall effect of the nutritional challenge. We had we considered 5 variables, 2 performance traits, including milk yield and body weight, 4 blood metabolites, including non-esterified fatty acid, glucose, and beta hydroxybutyrate, and urea. The analyses were done in 2 series. The first series was for data from pre-challenge, challenge 1, and inter-challenge periods. And the second series was for inter-challenge and 3 successive challenge and the pre and post-challenge. The model that we have used for this analysis was including days relative to the start of first challenge as the fixed factor and the cows as the random effect. We have tested 3 covariance structures: compound symmetry, autoregressive, and spatial power. And the best covariance structure was chosen based on the lowest BIC value. Here are the results of the repeated measure analysis for milk yield and NIFA. The graphs in the first line are for milk yield, least square means for the milk yield. The graphs in the second line are for NIFA concentrations, and the last plots are the average dry matter intake in kilogram. In brief, this analysis showed that milk yield during the feed restriction decreased gradually, and it recovered gradually during the recovery period. We have found the reverse behavior for the NIFA, and it increased during the feed restriction period, and it decreased and tried to come back to normal level during the recovery periods. And we have found that the change in NIFA levels were more evident than the milk yield in response to the nutritional challenge. Following in one step forward, we have done the piecewise analysis with main objective of analyzing responses to feed restriction challenge at the individual level that can potentially help us to figure out variation between animals in response to feed restriction challenge, and also evaluate repeatability of responses, and as well as clustering animals based on similarity of the responses to the nutritional challenge. And for this analysis, we have followed the 2 references that you can see here. First, I needed to show an example of the analyzed data for the single challenge for one animal. As you can see, the numbers are showing. I divided the single challenge data in 4 parts. Part 1 for the pre-challenge period, part 2 for the feed restriction, and part 3, part 2 for the feed restriction, part 3 for the recovery, and part 4 for the inter-challenge with ad libitum diet. The point is that for each level, for each part, I have calculated a separate level and a separate slope. But however, level and the slope coefficients were representing the change in compared to the one previous period, which makes this model to be continuous. And this is done thanks to the dummy variables that I consider today in the data set, which is based on the methodology of the second reference that I present. Here is the theoretical form of the model. In the model, we have the mu, which is the mean or level of the pre-challenge or inter-challenge period. And we have assumed that in the pre-challenge, we don't have a slope, and we consider the constant mean value. Delta L is the change in the level of the upcoming period in compared to the one previous period. And delta S is the change of the slope in the upcoming period. And the other variables are actually helping us to fit the model for all periods at the same time. We have considered the animals as the grouping factor, and a maximum order of 2 was considered whenever it was necessary based on visual inspection and the resulted coefficients. Here are the predicted response trends of animals for NIFA. I dropped the other traits because of the time. And the graph in the left is for single challenge, and the graph in the right is for 3 successive challenge. I have found a high correlation of the 0.95, around 0.95 between the predicted and observed measurements, and which is indicating that the model well fit. We have also observed the high consistency of the trends obtained using piecewise regression with the trends of the least square means obtained from the repeated measure analysis that we have got another confirmation. In order to assess the average rate of level change in response to feed restriction, I have used a regression of the level change in a given restriction period and the level change of ad libitum or recovery period. And the reverse regression model was used to obtain the average rate of level change in the recovery period. And these tables are showing the coefficients that we obtained from the regression models. As you can see in the plot and the table in the top, the coefficients for milk yield are all negative, and the coefficients for the NIFA are all positive. And this table is the average rate of level change after feed restriction. Essentially, this coefficients means that their milk yield decreased during the restrictions, and it had an increasing trend. And all were, except one, all were significant in 5% level. And the positive coefficients are indicating that the NIFA increased during the feed restriction. And we have got the same results from the repeated measure analysis. The table in the bottom has the reverse coefficients, and we have positive for the milk yield during the recovery, increase of the milk yield during the recovery periods, and decrease of NIFA during the recovery periods. In summary, the experimental design that we have used was relevant to assess resilience and robustness characteristics in Charolais suckling cows. Feed restriction decreased milk yield with a concomitant increase in plasma NIFA concentration. The continuous piecewise linear model could describe overall rate of change of milk yield and NIFA concentration. And the piecewise models that we have used can be considered as an optimal approach to detect different response trends of animals. As the next steps, we will perform clustering approach based on the results of piecewise analysis. And after that, we will seek for a possible relationship between clusters and the feed efficiency trait, which is the residual feed intake. Yeah, thanks for your attention.
Cheers. Thanks, Amir, for presenting your work, and apologise for the slight technical hitch. We've just got time for a couple of quick questions. If anybody's got a question from here.
Hi, thank you for the talk. I understand that time was limited, so you couldn't say very much about the resilience parameters and the residual feed intake. But I asked the question just in case in a couple of sentences you have something you can tell us. Is there a relation between the two?
Yes, well, the analysis just recently finished, and we will actually, after this meeting, I will go through them. We have the 3 category of RFI, and they are changed, and it is normal to they change. We will first do the clustering, and then we will see the relationship. But until now, no, I have not touched the RFI data.
Okay, thank you.
Cheers. Thank you, Amir.
Thank you.
Third presentation is from Harriet, the effects of climate on beef cattle. Can I ask Harriet to come forward?
Okay, thanks, Angela. So moving on from potential resilience to nutritional challenges in beef cattle, I'm going to talk today about looking at how we might see resilience for kind of effects due to weather or climate on beef cattle. And the real first step of this was, before we can start talking about resilience, we have to know as a whole, how are beef cattle actually affected by weather? So that was where I started, and that's the results I'd like to present today. Okay, so this is the main question I really wanted to answer, which is, how does weather affect growth and carcass traits in UK beef cattle? I had access to some really great data to answer this question, so I'll quickly go through that. First of all, I combined the location of each animal within both the data sets. That was from the BCMS database, with the daily weather that we would expect there to be at that location from the Met Office HAD UK grid database, which is publicly accessible. And that gave us the weather that every animal experienced every day across its lifetime, which is obviously quite an overwhelming data set. So I started off by simply doing averages across the life of the whole animal. So the 3 parameters that I had from this weather database is daily maximum temperature, daily minimum temperature, and total daily precipitation. And I simply took those and averaged it across the lifetime of the animal to see, can we see any kind of broad trends? Also, from that initial data set, I calculated the total number of extreme days, so this is cumulative, across the lifetime of the animal. When I'm talking about extreme weather days, I mean, so there's some that are to do with temperature. So we've got heat waves and cold waves. These are at least 3 consecutive days of temperatures either over or under a threshold. For heat waves, I used threshold determined by the Met Office, and that's maximum daily temperature has to be over that threshold. And for cold waves, I stuck with the threshold of just 0. So we're talking below freezing. Then looked at extremes of rainfall, and for this, changed kind of definitions quite a lot, but in the end went for just the 10th and the 90th percentile for the threshold. So very wet days are over the 90th percentile, and very dry days are below the 10th. So that's the weather. Now let's look at the information we have actually about these beef cattle. There's firstly this brilliant database that we have, which is this UK abattoir database. It's a huge number of animals. By the time I did my data cleaning, got over 1.6 million animals that were alive between 2000 and 2019. And for them, from their abattoir record, we can extract a large amount of data, but particularly I'm interested in their coal carcass weight, their fat and conformation scores, which are on a scale of 1 to 15. And we also, from this, can look at their age at slaughter. And I calculated this sort of growth parameter here, which is simply the coal carcass weight divided by age at slaughter. To go alongside this, to look at specifically one section of an animal's life, I had access to the Scottish Beef Efficiency Scheme data, which is information about calves in Scotland. I had a data set of over 270,000 calves between 2016 and 2019. And we have this trait that's called 200-day weight. But as you can see from the histogram here, it's actually, the weight is taken at quite a range of different days. So as well as this trait, I also again looked at a kind of growth trait, which is actually just weight divided by age when the weight was taken. So to go on to how this data was actually analysed, this is the general model that was used for all the different analyses, where I modelled each beef trait individually. Firstly, I'd modelled it including all of the average daily weather, and then I did a model for all the extreme weather. And the important thing here is that when I was modelling one of the carcass traits, I would put in the other carcass traits as covariates, because that's been shown to be quite important. This data has been analysed for a number of reasons in the past, and that's always been quite important. For extreme weather, I fitted age as an interaction effect, because animals that are older are more likely to have experienced more days of extreme weather. And for daily weather, I fitted interactions between those weather terms. So daily minimum temperature and rain seemed to be important, and also this interaction between daily minimum and daily maximum. All this analysis led to a huge amount of results, and I really don't have time to go through everything today, but hopefully you can see a good number of these are significant, and some of them are beneficial and some of them are less beneficial. So just a kind of summary of all of that, although I'm happy to go through anything anyone's particularly interested in. If we're seeing increases in daily maximum temperature, we're going to see potentially some improvement in conformation, which is interesting, but a real decrease in, first of all, age at slaughter, this carcass growth trait, and then also calf weight and the calf growth trait. This compares to increases in the daily minimum temperature. We'd actually maybe see an improvement in terms of age at slaughter, carcass weight, again, conformation, and this time calf weight might be improved, but we might see poorer growth. Those are the two growth traits I looked at. And then finally, for rain, we can see that increasing rain might improve our age at slaughter, so animals will be younger, and might improve the carcass growth rates. But actually, we would see poorer carcass weight, poorer conformation, poorer calf weight, and poorer calf growth. Again, found some really interesting, significant results for extreme weather days. Fewer of these were significant, and that might be to do with some of the animals not experiencing very many extreme weather days. But to summarize that, it seems from these results, we might expect that more extreme weather days may result in poorer beef production. So for things like, on average, each additional day where the temperature doesn't reach 0, we might expect more than 3.5 more additional days till slaughter. And on average, for each additional day where the rainfall is currently above the 90th percentile, carcass weight will decrease by 44 grams. Now, that might not sound very much, but we're not expecting one additional day of extreme rain. We're probably expecting animals to experience many more additional days of extreme rain. But from these results with age fitted as a covariate, it looks like actually more heat waves might reduce age at slaughter, which might be a little bit not what we'd expect. And maybe more dry days, more really extreme dry days, might increase carcass weight. So that's it from the results I'm going to share with you today, but I'm going to talk now a little bit about what I would like to do next. And I think these results, there are a few different ways we can go with them. We can go, okay, well, what do we expect? How do we expect the climate to change? Therefore, what would we expect to happen in beef production? And I'm really keen to do that. But I'd also like to look for, okay, we're seeing these effects of climate, what can we do to try and mitigate them? And there's definitely the management aspect, and that would potentially be really interesting. But personally, I'm also interested in the kind of genetic aspect. So to look at that, to see if there's genetic variation for resilience for beef cattle in terms of climate effects, I want to look at, see if there's variation in how certain groups are affected by weather. The first place to start with this seemed to just be to look for a breed by weather interaction. I've got breed in the data set. Let's just see how that works. So I grouped breeds, and we often do this in the UK, by native UK breeds, continental breeds, which tend to be the breeds that require more inputs, and then dairy breeds. You can see here, so A and B, if they have the same letter, that means that they're not significantly different from each other, but if they have different letters, then they are. So we can see that generally continental and dairy breeds seem to be responding differently to weather. And that's potentially interesting, but it looks like weather has a greater effect for continental breeds. My question is this a management effect? Is this real G by E, or is this actually just dairy cows are more likely to be kept inside? So that's definitely going to be an issue going forward with my analysis. One thing that I think was potentially interesting is that if we're looking at the effect of rain, so this is age at slaughter and carcass weight, just those two traits, there was a significant difference between how continental and native breeds were affected. And here I could see that maybe native breeds would be less affected than continental by weather. And perhaps this could be a genetic effect. But again, it's just really hard to separate the two. So I think my next step, ideally, I'm going to really try with this data set. I have so much data, it's very noisy, but I have an awful lot of it, to see whether we can do a within breed analysis and look to see whether, obviously the problem with beef data is that I don't have lactation yields for, or milk yields for every day of the lactation. I just have one phenotype at the end of life. But I'm hoping that maybe within sires, I might be able to try and do a kind of reaction norm style analysis. But that's my aim, but I'm be really interested to hear if anyone else has ideas about a better way to look at this data set. And that's it. Thanks for your attention.
That's brilliant, Harriet. Thank you very much. Has anybody got any questions for Harriet?
Yes, I've got a short question. So was the humidity the same across the different heat waves?
Unfortunately, I did not have humidity data. I would have loved to do humidity, because then I think I would ask that question if I had listened to my talk. So unfortunately, I didn't have the kind of resolution that I needed for humidity data. I think it might be less variable in Scotland than it might be in other places, but it still does vary, and I don't know.
Thanks, Harriet. Really, really interesting. Keen to kind of link up on it more. Just I know it's kind of initial work to some degree with bits, but just your impressions. Do you think there's a bigger variation intra-breed or interbreed in what you're seeing between those things? Just how big is the variation within breed? I'm just interested. Are there genuine breed effects, or actually have we got much wider variation than that?
The variation of how individuals are affected. I don't know how I would, that's what I'd like to measure, but I can tell you how the group are affected, but how individuals are affected is what I haven't worked. Yeah, that's what I'd like to do more.
Thank you for the presentation. Can you precise what is the management system regarding whether when it trains the animals are indoor or outdoor, generally speaking?
It varies hugely, and that's why I had that contemporary group effect in, because without the contemporary group effect, the results are wildly different. And so that contemporary group is, there's the birth herd year season, and then there's the finishing herd year season, which is the last 60 days, an animal, where they are for the last 60 days of their life. And that's trying to account for some of that variation in management. But that's sort of why I asked the question from the first talk. It's a bigger problem in beef, because I think we have bigger variation in management, and we definitely have confounding between breed and management. I don't know if anyone else wants to comment on UK beef production, but my experience is it's very variable.
Yeah, there was a result which I was struggling to get my head around. I think maybe I saw the table wrong, but it seemed to say that if there was more rain, there was an improvement in one of the growth rates. That was on your summary table.
No, that's the wrong way.
Maybe I saw wrong. Yeah, that one. So is that right? More rain gives, okay, an increase in age at slaughter, I can understand that, but gives an increase in that adjusted growth rate?
That's to do with the effect on carcass weight being stronger than the effect on, oh, hang on, no, the other way around. That's to do with the effect of age at slaughter being stronger than the effect.
Okay.
Because that, can I make it do the thing? This is just this divided by this.
Okay.
So this, the effect on this is quite small and the effect on this is quite big.
Thank you, that helps. I thought we were going to have a recommendation that we should water animals more to make them grow faster, but that's not the case.
I didn't have time for the discussion of that, but I'm really interested to understand the mechanism behind some of these results and how much of its management and how much of it might be to do with parasite load or feed availability. I don't know any of that, but it's really interesting to have discussions about it, about why we might expect to see these results.
Brilliant, Harriet, that's lovely. Thank you for presenting your work. Okay, I'd now like to ask Rasmus to join us. His presentation is on genetic components of a dynamic RFI model in multiple lactations.
It works? Yeah. Yeah, thank you. Right, so this is the second part of my presentation. So continuing from yesterday, so also states volume 2. And I again like to thank, I'll stand here so I don't have the light. I'd like to thank the group that's helped me on this, both with data and the analysis and creating this presentation. So the aim of this presentation is to estimate variance components for a dynamic RFI model. And I'll try to go through, or the outline is looking at some pedigree links, the genetic model, some results, and then finally some conclusion and next steps for my research. And just a reminder from yesterday, because of course you all remember in detail what I presented to you, but just in case you did not, we had data from first and second parity on 1100 or near to 1100 Holstein cows from the Follum herd in Denmark and the Gerbrich and Picasso herd in France. And the data looks good and is ready for genetic analysis. And looking more into the pedigree, it was pruned for 8 generations. We did not see any common sires between the two, between France and Denmark, but it was also kind of expected. But we see 14 common grandsires, so there are some links, and you see in the table that we have the 14 bulls and then the number of offspring in the Danish and the French herds. So we have some bulls with offspring in both herds. So that's good. And for animals with missing parents, I included genetic groups with an effect of breed, and country, and the year of birth. And now more into the genetic model. So what you see here, we have a genetic model for dry matter intake, energy corrected milk, and body weight, and we have it in first and second parity, so it's independent trait for parities. What you see, we have Y is the trait of interest, the herd year season is the fixed effect of herd year season based on calving date. Then we have an effect of weeks of lactation, so it describes the lactation curve. Then we have age of calving and age of calving squared, only in first parity. Then we have an rth order of Legendre polynomial on the additive and permanent environmental effects, and we fitted it first order in for DMI and ECM, and a second order for body weight. And then there was a random effect to account for the experiment, so what the cows were undergoing at the experimental farms, and then a year-month effect from random year-month effect from the record date. And important to note here, the residual of this model was assumed to be heterogeneous across lactation periods, so we allowed it to change during lactation. And then how was the analysis performed? We used DMU with the AI REML algorithm and also the EM algorithm. So first, models that did not meet the converge criteria in DMU with the AI REML was changed to EM. That was 5 out of 15 models. However, still the EM algorithm could not meet converge criteria, but they could give a result that was more meaningful. And to construct the whole covariance structure for our 6 traits, so we have 3 traits in 2 parities. There was 15 bivariate models. And of course, with more data, I'll try to test more advanced models with more traits, but this is how I try to do it here. And then I constructed an overall G matrix containing not the genomic relationship, but a G matrix containing the variance components. It's very important, this one. And I calculated the simple averages from the different bivariate models. Of course, the covariance parts, they are only from one model, but you can imagine that, for example, DMI in first parity, it is common for 5 models, so there's a simple average over these 5 models. This overall G matrix, called G0 in later notation, were not positive definite, and which will, you will see, influence my results. So just to show you some notation about how I derived my output or get my results. So I followed the notation by Islam et al. From 2020 and Martin et al. From 2021. So to get the genetic variances for the specific week, so W means weeks of lactation here, you have the phi matrix times the G0 from the previous slide times the phi transposed. How do they look? Well, you have the variance components here. So on the diagonal, you have the variances of DMI, ECM, and body weight. And then on the off diagonals, you have the covariances. And please also remember this notation about dividing it into 4 groups. That makes more sense in the next slide to calculate regressions. And then we have the phi matrix containing all the Legendre polynomials. There you see in the upper left corner, we have the intercept and the linear effect for DMI. Then next you have ECM. And then for body weight, we have a quadratic term. And then you might think, what is the next? That is actually a quite nice way to derive the change in body weight. So we take the changes between 2 weeks for the Legendre polynomials. And by multiplying the matrix, then it means you actually take, you can derive delta body weight from the slope of the core trait, in this case, body weight. So then we do not need to estimate variance components for delta body weight or change in body weight, but we can simply take it from the core trait, which I think is a quite nice property. And then parity here is only considered one parity, but if you can simply just add more parities with block elements. And here's the matrix of interest. So we like to derive. That is a matrix also where we include residual feed intake. So how do we do that? We take the B matrix that's containing regressions, I'll show you in a minute. And then the G matrix I showed you previously in times the B transposed. And the B matrix simply looks like this. So a matrix containing all the regressions for the specific weeks of lactation. So, and then how to derive the regressions, that comes back to what I told you on the previous slide. You could see here that we have the regressions are equal to the B21 times the B22 inverse. And then you could, if you want the genetic or phenotypic regressions, you can simply just use the G or the P matrix respectively. So it works quite nice. And here's some results for the heritability and additive variance. So what you see, the solid line, that is the additive variance. So blue represent first parity, green second parity. And it's around the level 0.5 to 1, the additive variance. And if we look at the medium dashed lines, that is the heritabilities, which in first parity starts around 10% and increases to late lactation to 20%. Where in second parity, we have a quite stable level at 20% of heritability. And if we try to compare to Islam et al., he only used first parity animals from Folum. So there's a difference in the data. We see around 10% of heritability, or close to, also in the end to 20%. And if we also, the yellow line represents the additive variance from that study, and it's also have the same pattern, almost same level as what is found here, even though there's more data in this study that we did. Then we can also see some of the results that we have a not positive definite G matrix, because if we look at the correlations, additive correlations across parities, and if you look at DMI, you might see the blue line goes out of the range. So it goes up to actually 1.08, but that's caused by these models that do not meet the converge criteria. But if we look at the red line, if you try to focus on that, it starts at 0.6 and increases to around 9 mid and late lactation. That is quite close to what we should expect. I put in here 0.8 from the Nordic genetic evaluation is the correlation between first and second parity. And if we look at body weight, we expect it to be close to 1 because heavy animals from a genetic point of view in first lactation is also expected to be heavy in second parity. And we also see a quite high correlation here in this study. And looking more into the regressions, if you remember from yesterday, I put in some expected regressions. Those for ECM is represented as the red line. And sorry, on the y-axis, you see the regression, so the regression level, and on the x-axis, you see the week of lactation, if you can't see it from the back. And if we focus on the red line, we could see that actually the ECM regressions get quite close in both first and second parity to the expected level, or at least it's higher than what I've seen reported before. And if we look at the blue line for maintenance, it's very close to what we could expect. So that's quite nice. And if we look at delta body weight, I mentioned yesterday, I would like to work more on the expectations. But if we look at where the curve changes in first and second parity, it's around 20 weeks of lactation, which is pretty much close to where the energy balance goes from negative to positive for the animals. So some conclusions and next step. We have estimated variance components for genetic RFI. We are challenged on the data size, but as I mentioned yesterday, that is something that will be improved in the next month. And the next steps, yeah, we'd like to run, of course, these analyses with more data, also include third parity. And I think also third parity will be first included when we can run analysis with more or run models with more traits, because otherwise the number of models explodes. Also do heat maps or the genetic architecture of genetic RFI. And then also focus on these expectations to regressions and then put all this together, hopefully in a World Congress paper for next year. So that was it from me.
Brilliant, that's lovely. Thank you very much, Rasmus. Have we got any questions for Rasmus now?
It was crystal clear.
Ah, look, you escaped. That's lovely. Thank you very much.
Okay.
Have you considered bending the first approach would be to try to bend your genetic covariance matrix. Have you tried that in order to remove the singularity?
Yes, we have considered it. Well, we think it was worth waiting for running the analysis with more data, because the next step is, so we have access to much more data. So we'd like to do that as a first step. And then, of course, if we still have problems with the G matrix, and as you mentioned, then you could think of bending it. So yeah, so it gets a positive definite.
Any further questions? No, that's brilliant. Lovely. Thank you. Cheers. So I'd like to ask Alban to join us now. Brilliant. Okay, so the presentation next. What can we gain from mechanistic models to predict selection response on lactation efficiency?
I will just. Good.
Tap down to go to your next slide.
Yep, okay. Good. So my name is Alban Bouquet. I'm a postdoc at Aarhus University. So I'm mainly involved in work package 5, which deals with breeding strategies. So the objective of my postdoc is to see how we can use all the mechanistic models developed in work package 6 in a kind of breeding perspectives. And here I will show you how we can use those models to predict selection response. So this work is a collaboration between Aarhus University, Viking Genetics, and INRAE. Good. So the Gentor project is all about breeding for efficient and resilient cows. So efficient to reduce the environmental footprint of their reproduction, but resilient to breed also cows that are adapted to the environment. And it's all about finding the right breeding strategies to find this balance between resilience and efficiency. And this is the objective of work package 5. But to be effective or successful, all those breeding strategies must keep in mind that they have to be environment specific to match the diversity of production systems and production environments we have in Europe. And we also must anticipate some changes in the environment. So it can come from climate change, but also from societal demands for example, more grazing. So generally, when we want to compare breeding strategies, we predict the genetic gain that could come from such strategies. And to do that, so we need to have some genetic parameters for the traits we want to select for. So this is a G matrix. And we have to describe the breeding scheme structure and the breeding goal. So generally, we do that with some software. Here, I will use Adam. So yeah, and based on that, we can predict genetic gain. But those genetic parameters are estimated within one environment. And so is the prediction of genetic gain. It's just valid in the considered environment. So if we want to compare breeding strategies across a wide panel of environments, we need to have genetic parameters within each environment and across environments. So it increases quite much the number of parameters and the computational burden. And sometimes we do not have those genetic parameters because for some traits, some new traits, we do not have enough data, or for some environments, we do not have the data. So here in this talk, I will show you how we can capitalize on some new mechanistic models that were developed in work package 6 to predict selection response. So given the time allocated to this presentation, I will just give you the basic principles and an illustration with a small example. So this work is all based on the mechanistic model developed by Lawrence and collaborators. So the objective is to model how a cow will respond to a nutritional challenge. And the basic idea is to think that this response will be conditioned by the way the cow will acquire energy and partition this energy. So this mechanistic model is a compartment model, and it describes how energy will flow in the system and how energy will be channeled to the different functions. So we have those here, acquisition parameters, which will describe how energy flows in, and those allocation parameters. So it will describe how energy is channeled to, for example, lactation, growth, gestation, or for other functions. One big assumption we made is that some of those parameters are controlled by genetics. And the green arrows are those ones that are genetically driven. Another assumption is that those scaling parameters, acquisition allocation parameters, are independent from the environment. What I mean is that when, for example, one cow has a high allocation to lactation, she will have a high lactation allocation, whatever the environment, low or high nutritional environment. So this model was implemented in a simulation tool called AQUEL. And this tool, so based on a given nutritional environment and those acquisition and allocation parameters and the model, enables or allows you to simulate some phenotypes, phenotypic trajectories for different traits, so milk production, bony mass components, you have also dry matter intake, etc., over the lifetime of the animal, so from birth to culling. And in a recent version of the software, it is also possible to simulate some pedigree or population structure. And this allows you to do some genetics based on the simulated data, which is quite nice. So this model was calibrated by Lawrence to simulate some realistic data sets. And we also performed some sensitivity analysis to better delineate what should be the genetic parameters to use for those genetically driven parameters. So now we have a software, a model, a software to simulate data. I will describe now how we predict selection response. So the basic assumption, again, is that when we do some selection on lactation or functional traits, actually we change the genetic level of this acquisition and allocation parameters in cows. But if we are able to estimate this change in nutrient partitioning strategies, actually, since they are independent from the environment, once we have this genetic gain, we are able to resimulate new data based on what should be an improved cow. So since we are not able to derive all the genetic or variance components for the simulated traits based on the acquisition and allocation parameter or genetic determinism, we use simulation. So we have those initial parameter, we use the AQUEL software, and we assume some environment to simulate some data. We use this data to estimate the genetic parameters
between the acquisition allocation parameters and the traits of interest. And we can use those genetic parameters in ADAM to simulate a breeding scheme. And with ADAM, we can predict what should be the genetic change in terms of acquisition and allocation. And then once we have this genetic improvement in terms of acquisition allocation, we can use AQUIL to re-simulate new data, for example, in the same environment. And the difference between the initial situation and the one after a selection is your selection response. But you can do this in the same environment, but you can also simulate data in another environment. So to estimate selection response done in a breeding environment in another environment. So now I'll just describe a small example. Typical breeding scheme of dairy cattle, 20,000 cows, 100 sires. I modeled, so plus those 4 acquisition allocation parameters, and I considered milk production, body weight, lactation efficiency, and a fertility trait. I defined a breeding goal with kind of balance between milk production and fertility, with some weight on the body weight to have something stable. So I simulated the data with AQUIL, considering a nutritional environment, which is kind of a low input grazing system. And I use this data to estimate the genetic parameters, and I use those genetic parameters in ADAM to simulate the breeding scheme over 25 years. And I estimated the genetic gain on both the acquisition allocation parameters and the traits in the breeding goal. Now I will just come to the results. So here you have the genetic gain estimated with a conventional approach. Genetic gains are in line with expectation. So some genetic gain on milk and fertility. So reduction of the interval between first and last insemination, conception. What was quite interesting is that with ADAM, we can now estimate also what will be the response on the nutrient partitioning strategies. So even though we improve milk production, actually we can see that most of the genetic progress was done on this allocation to body reserves. So we'll produce more milk, but with cows able to store more body reserves. So to have good reproduction, and they will be able to use those reserves also for milk production. So if then we use this genetic gain on allocation acquisition parameters, and we resimulate data with AQUIL, here I will present you the results we expect annual genetic change. They are quite consistent for milk production, body weight. What we can see, we have just a slight higher genetic gain in the conventional approach for the fertility trait compared to the new approach. But things are consistent. So now just a few conclusions. So here I presented you some new flexible modeling approach for benchmarking different breeding strategies, breeding scenarios. Within environment, we got some consistent predictions between the 2 approaches. And now we have to explore a bit more to see if there are some situations where it works, but also it doesn't work. So as said before, this is now so possible to simulate performance for improved cows in the same breeding environment, but also in other environments. So it could be of interest for work package 6 to predict the profile of a future cow based on a given breeding goal. There are several benefits of this approach compared to the standard approach to predict selection response. So it's more efficient, but also you have a better biological insight because you have information also on how the cow will partition energy through the different functions. And something we have to keep in mind is that those predictions really rely on a model and its capabilities. So right now, AQUIL is only able to simulate data following a nutritional challenge, but there will be new possibilities also when new modules will be available in ECHO. So this is it.
That's lovely. Thank you for your presentation, Alban. Has there anybody got any questions from the floor?
Me again. Already this morning, I was wondering why you're assuming that gestation is not genetically controlled. So this is one of your allocation parameters, but to say the arrow was blue, so that means there's no genetic control over gestation.
Maybe Lorenzo will have. I will need a bit of help. I guess they in this model they really focused on the sinks or parameters on which there will be a lot or more variation, more variability. But yeah, I don't know, Lawrence, if you have some more input on that.
Of choice, we choose to not introduce or consider that the parameter that is controlling gestation as a genetic background. But if one day, currently ACAL is calibrated for beef cows, and of course we can consider that the genetic background is at this level. But choosing that the parameter as a genetic status in terms of background is really a choice of the modeler. So if we have good reason to consider gestation is under the genetic control, and we are interested in investigating the variation in these parameters, that could be a possibility. But here for this study, with already 4 parameters that it's not always easy to interpret the results, we choose to keep that simple with 4 parameters of interest for the dairy sector.
So have we got any further questions? Brilliant. That's lovely. Thank you very much. Okay, can I ask Dyan to join us now, please? Thank you. So this presentation is the identification of risk factors for insemination success in dairy cows.
Oh, yeah, that's it. Okay, thank you. Okay. So hello, everybody. My name is Dyan Meuwissen, and today I will be presenting some of the work that I did during my, I am currently doing in my PhD together with a master thesis student of our group. I don't have any direct contribution to GENTOR or indirect contribution, but some of the future work that I really want to do during my PhD, it is in the context or the same mindset as GENTOR. So I'm really happy to be here and to learn from you all. I thought first maybe a personal introduction because I'm quite new to the whole group. I started my PhD last March. And this is me, not holding a cow, unfortunately, but a puppy will do. And many of you have been asking, are you from Wageningen? Are you from KU Leuven? Because I'm hanging with the Wageningen people. But I actually did my master's and bachelor at Wageningen University at the Animal Breeding and Genetics group. And I did my master thesis in multi-population genomic predictions, so really on the genomic side. And then I did my master internship at Trouw Nutrition, which is a feed company, in which I really dove into the phenotypic sensor time series. And I actually based my research on the research of Ines in the context of GENTOR about lifetime resilience score. And I learned from that research, and I also had a couple of my supervisor set up a collaboration with Ines and with Ben from KU Leuven. And so that's how I ended up at the livestock technology group at KU Leuven, which you see in the bottom, and I really, really like it there. So my current work has been also focused on writing projects because I still need to get my own funding. And all those, yeah, Ines helped a lot with those projects. So they're really influenced by her ideas, by her experience, and also for my own affinity with animal breeding and genetics background. And those projects have been mainly focused on dairy cow fertilities, really trying to predict the conception rate in dairy cows. But with this, not being afraid to move between disciplines, really including the genetic side and the phenotypic side, but also making the right combinations between different phenotypic sensor time series. So not only looking at progesterone, but really placing the performance of a cow, her health, her performance, what we would expect of the cow based on her genetic background, and really seeing how this would affect fertility performance. And I really hope to being able to study this in the future. I had my defense last Friday, so hopefully it went well. But of course, I was able. Okay, doesn't matter. I thought I had something in between, but I was able to already start looking at fertility, of course. So I made a start by looking at the basics of fertility, and that is with progesterone. So for what can we use the progesterone concentration in milk? Progesterone actually reflects the fertility status of a cow, and more precisely, it reflects the presence or absence of a corpus luteum. So after ovulation, a corpus luteum is created, it produces progesterone, and when this corpus luteum regresses, the progesterone concentration drops, and we can use this moment to indicate timing of luteolysis, so that's a drop in progesterone, but also timing of ovulation, and to see what is the correct window for insemination. And of course, when you want to implement or use milk progesterone on a farm, you need to have an online monitoring system on farm. So with every milking, a sample is taken from the milk robot and the progesterone concentration is analyzed. And there is actually a commercial available progesterone monitoring rhythm already being implemented on farms. And this is Herd Navigator. And what it does, it actually has the raw milk progesterone measurements, and it smooths the values. And when this smoothed value goes below a fixed threshold, so 5 nanograms per milliliter, then a luteolysis is identified and the insemination window can be correctly identified. And this system is really valuable. However, there are a few drawbacks. So for example, the first one is that it uses a fixed threshold. So that means it's not able to cope with the variability between cows, but also not within a cow between cycles. And another major drawback is, if you look at the second complete cycle in that picture, is that it needs 2 raw progesterone measurements below the very low measurements to be able to have that smoothing below that fixed threshold. And when there could be a problem that the cow is not going to the milk robot or that the biomonitor is not working. And then, for example, the first raw measurement here was 3 days before the second one. So that means that actually luteolysis is estimated to be 3 days later than it actually happened. And this is, of course, not good for identifying the insemination moment. So what me and also my thesis student, Kim Brozens, were thinking about investigating was identifying those risk factors for insemination success, but not using the Herd Navigator model, also using a model that Ines developed during her PhD. And this is actually the progesterone monitoring algorithm using synergistic control, also named PMASC. And then seeing the potential of using PMASC versus Herd Navigator, because we have a few farms that we collect data of, we have a collaboration with them, we see fertility issues at this farm, and what would the potential be, or what could PMASC mean for those farmers instead of Herd Navigator, for example. Then deriving features from the PMASC model on the progesterone measurements. Then identifying those risk factors for insemination success. And in the end, also combining or doing an easy integration of the milk production dynamics. So maybe perturbations, the moment of insemination, was there a perturbation present? And using those values also see what is the effect on insemination success. Some of the basics of the working of PMASC. So you have the first four raw P4 measurements. You can fit an initial model on them. And every time a new measurement becomes available, the model starts updating. But it's first checked if the measurement is within the control limit. So it uses a control chart to check if it's okay to update the model. So new measurement is added, the residual is checked, it's okay, it can be included to update the model. And this is done with each point that is available. It's all within the control limit, so it's okay. Can update. And then there's the first measurement that's out of control. That measurement is not included to update the model. The second measurement also out of control, not included to update the model. And then when there's a third measurement that's out of control, it's identified as a luteolysis and the full model can be fitted. So in the end, we will have a progesterone profile with all different cycles, with all different characteristics, with all different parameters to fit the full model. And we can then use that model to derive those characteristics from the progesterone profile. But of course, the problem here exists as well with sample frequency. So we need a robust parameter to identify that moment of luteolysis. And also Ines investigates several parameters and identified this one to be the most robust one. It's the 85% of the maximum value of the model minus the baseline, so that's P1 parameter. And then when the full model drops below that threshold, the moment of luteolysis is identified. So here's the parameter is 4.48. And then you can see the moment that PMOSC identifies luteolysis is 73.7 days in milk, and the actual raw measurement was at 73.8 days in milk. So it's really close to each other. And when we combine it with the working of herd navigator, that's the dark blue smoothed value, you can see the moment of luteolysis based on the smoothed value was estimated at 76.6, while actually luteolysis already happened 3 days before. So I was really investigating in this, okay, what does that sample frequency mean? And can we use that to also give an advice to the farmers that we have that collaboration with? But it's actually really difficult to get a good grip on that, because it's not only the sample frequency that says, okay, this is a successful or unsuccessful insemination, it's far more characteristics. So I wanted to correct actually the inseminations that I knew for sure were not inseminated in the correct window. But of course that was really difficult because farmers write down insemination based on day and not an hour. So there are some limitations in that and with which I have to deal with. So I had several selection steps of excluding inseminations that were for sure not in the correct window, and also the inseminations that were that resulted in embryonic mortality. Yeah, and this gave me in the end access to 4 farms with these numbers of successful and unsuccessful inseminations. They're not an indicator of how the fertility performance is at those farms, because like some farms have a different sample frequency than other farms. So, but this was in the end what I included. So now the next step, deriving some progesterone features from that full model that we fitted. I only looked at a few, or like my thesis student also looked at a few, because yeah, it's difficult to get a grip on those, as I already said, and I will show in the next slide as well. But I looked at cycle length, so it's the pink arrow is the moment of insemination, and it's everything that happens prior to insemination, because of course you want to identify, is this the correct moment to inseminate? So I looked at the cycle length previous to insemination, because it could be an indicator of, for example, embryonic mortality before the insemination. Or I also looked at consecutive days below 4 nanograms per milliliter, or consecutive days before more than 50 nanograms per milliliter, which could indicate a follicular cyst or a luteal cyst. These were the first results of cycle length. And as you can see, I didn't do any significant tests on it. It already shows that there are small differences between unsuccessful inseminations in light blue and successful inseminations. But I think I need to look into more depth in that characteristic and also see which inseminations to include. I need to maybe include that sample frequency to make that right distinction between correct window or not correct. And also some results of the consecutive days below 4 nanograms a milliliter and above 15 nanograms a milliliter. Also very little differences between successful and unsuccessful insemination. So as you can already feel that, of course, I need to investigate it more. I need to derive more features, look more closely into those features, maybe include sample frequency as really a strict boundary, or how to use that herd navigator versus PMASK. But I really do believe that fertility is really complex. And in order to really understand what is going on, we need to include more than just parameters from progesterone. We need to include the health and the production of the cow and make this link with fertility. So Kim, the PhD student, is going to look into how to include the perturbations and a milk production into finding a difference between insemination success or no success. But then we really need that genetic background. We need to place that cow within our own farm context to see what can we expect from this cow based on her genetics, and how does she actually use her genetic capacity. And I really hope to pursue this in my future research. That was it. Thank you for your attention.
That's great. Thank you, Dyan, for presenting your work. Have we any questions from the floor?
Thanks, Dyan. It's really, really nice work. I think it's really interesting and such an important topic. So I think there's loads, there's lots of things to do, which is really exciting. I'm really interested in your data set about pregnancy loss, because I think it's so important. We know maybe 30% of twin pregnancies are lost, by maybe 100, 110 days, around 5% of single pregnancies. So if we can identify that as an intervention, so I'm just really interested what features, both in progesterone, but also in other, actually in sense features, may alert for that risk of pregnancy loss would be really interesting to look at. So.
Okay, thank you for your suggestion.
That's brilliant. Any more questions? Brilliant. That's lovely. Thank you very much. Okay, can I ask Anna to join us now? So her presentation towards a single-step breed origin of Neil's model for genomic prediction in a multi-breed cattle population.
Okay, hello everybody. So my name is Guillenea. I'm from Aarhus University, and I will presenting some results of an ongoing project. The title of the presentation is Towards Single-Step Breed Origin of Allele Model for Genomic Prediction in a Multi-Breed Cattle Population. So during the presentation, I will briefly talk about the background of this model, the objectives for this specific part of the study, methods, data for genomic prediction, the models that we're going to use, and the validation of these models, and some preliminary results and take-home messages. So briefly the background, the generation of crossbred cattle, as Morten said, is increasing globally. And in addition, the low cost of genotyping has facilitated the collection of large amounts of genotype data, which includes information from crossbreds. But still, most of current evaluations are based only on purebred data. So there is crossbreed information that we are generating, but we are not using in estimating the marker effects. So here briefly an introduction about genomic selection. We have some population for which we can have, for example, the pedigree. Then usually a small part of this population has genotypes, and we have some phenotypes, for example, carcass weight. And then with the model, we can have the association between the marker and phenotypes and use it to predict the performance of newborn calves. So it works really well in single breed evaluation. But what happens in multi-breed populations? From a biological point of view, makes more sense to think that they have the same allele effect across breeds, or that the alleles are breed specific, the effect. So then there has been a couple of recent studies in which they estimate breed specific allele using purebred data. But in our case, what we're going to do is to estimate also breed specific allele effects, but using an approach that includes both crossbred and purebred in the reference. So we can have a larger reference population, and it allows for correlation between the breeds. So yesterday, INRAE presented some of these results. And the idea of this particular part of the project is to extend this BOA model to a case of, for a single step genomic model for a large population in which just a short part of the population is genotyped. And then we will evaluate the accuracy of these predictions. So now these are the steps. I will show you briefly the steps toward the final model because there are several steps. First, of course, we need to collect the genotype and phenotype data. In our case, we are using information from the Irish Cattle Breeding Federation. So we have the genotypes and phenotypes. Then the second step in this kind of models is that we need to estimate breed origin of alleles. And the software to do that requires to know the purebreds that are in the population. So then we can have some reference animals of these purebreds to trace back the allele of the crossbred animals. So in our case, in this multi-breed population, we identified 4 main breeds that are Charolais, Limousin, Angus, and Holstein. And then we group other minors breed in a group that we call others. So then we trace back the alleles to these 5 components. Then we run a model to correct the phenotype for non-genetic effects. We run another model that is this BOA model to estimate variance components using these models proposed here. So in this case, we're using animals that are both genotype and phenotype. And finally, we have this model that I will present now that are for this large population in which only a part of the population is genotyped. So I will focus in this last step. So the data I have for genomic prediction is really large. We have 16 million animals in the pedigree. We have the phenotype of 9 million records of corrected carcass weight from this previous step. And we have the genotype of almost 371,000 animals. So as you can see, it's only a small part of the population. The models that I will present here are the single step SNP lab and the single step SNP lab accounting for BOA that I call single step BOA. So basically the differences between these two is that the single step SNP lab requires the pedigree for the population, 1 matrix of genotypes for the whole population. So we're assuming that we have only 1 population, they all belong to the same, and 1 genetic variance. And then in this single step BOA, we will use the same pedigree, but we will use 5 matrices of genotypes, each with allele content from 1 breed, so Charolais, Limousin, Angus, Holstein, and these others, and with 1 matrix with covariances between the breed, variances and covariances between the breed calculated in the previous step. And we're also working on pedigree lab. For the validation of the model, we use paternal Hapsi families with a cutoff of birth year of the offspring of 2018. So here we have the time. So we have in the reference the old animals and the younger animals in the validation. And we calculate the accuracy as the correlation between the corrected phenotype and the breeding values. So now the preliminary results. This is the accuracy for all animals in the validation population. And they are divided for genotype animals and non-genotype animals. This orange is for a single-step SNP-lab, and this blue for single-step BOA. And we can see we did not test this significantly different, but the difference here is 14%, and the difference here for the non-genotype is just 3%. But in both cases, we can see that the single-step BOA is giving higher accuracies. Then this is for animals with 50% of one of these main breeds. So we have the first two columns, the first two plots are for non-genotype animals, and the last two for each are for genotype animals. So the first was is SNP-lab, single-step SNP-lab, single-step BOA, single-step SNP-lab, and single-step BOA. So red and purple are BOA. And we can see that there is an increase in almost all the cases, and the increase is higher for genotype animals. And the only case where we do not see this difference is in Holstein, 0.5% of Holstein, when there are more or less similar for the non-genotype animals. And then this is the accuracy of animals with more than 90% of one breed, and we see, more or less the same. The differences in non-genotype animals is not so high, but the differences in genotype animals is higher for BOA, for the use of BOA. And in the only case when we see that single-step SNP-lab perform better is for Holstein, more than 90% using, yes, for genotype animals. So as take-home messages, the model considering breed origin of allele has shown higher accuracies for this particular multibreed population in which most of the animals are non-genotype, but the benefit of accounting for breed origin of allele were higher for genotype animals. So what this means is that we can have more accurate breeding values for crossbred animals if we are including it in the reference and accounting for breed origin of alleles. So thank you for your attention.
Cheers, thank you, Anna. And do we have any questions from the floor? Oh, we get a cut. That's lovely. Thank you very much. Cheers. And for our final presentation this afternoon, I would like to ask Julie to join us. Her presentation is Crossbred Genomic Prediction using Summary Statistics.
Hello everyone, my name is Julie and I'm a PhD student at the Swedish University of Agricultural Sciences. Today I'm going to show you a little study that I did with Emma in work package 4 on genomic prediction in crossbred animals using summary statistics. There it is. So I assume that everyone knows the benefits of genomic prediction, so I'm not going into details of that. But the thing is that genomic prediction is used more and more also at the herd level. So farmers want to use genomic breeding values to be able to select future breeding animals among the heifers and thereby increase their genetic level in the herd. And I also assume that Morten managed to convince you that crossbreeding is great yesterday, so I'm not gonna try to convince you again, but if you're not convinced, we can talk later about that. Anyway, more and more farmers are convinced that crossbreeding is a good idea. But also now that they're also interested in this genomic breeding values, they also would like to have that on the crossbred animals. At least that's what I know from the farmers I have been talking to, that they are asking, when are you publishing that? And I still say, I don't know, but hopefully I can say they're getting here soon. So we have to work on that. And genomic prediction in crossbred animals is not as straightforward as it is in purebred animals, because purebred animals, they tend to look alike, at least genetically, because of selection and inbreeding, while crossbreds, they are different in their genetic makeup compared to their purebred ancestors. And also between crossbreds, they might be very different, even if they are on the paper, it should be on the same breed combination. So that's a challenge with that. So in order to, well, that's what Emma presented yesterday, and also Anna just mentioned it. In order to be able to get high prediction accuracies for genomic prediction in crossbreds, we need to combine pure breeds and preferably also crossbreds in the same reference. But there is a problem if we have breeds from foreign countries. So for example, we have the ProCross. ProCross is a very popular crossbreeding strategy around the world, getting more and more popular. So ProCross, that's a 3-breed rotational crossbreeding strategy between Holstein and the Nordic Red and Montbéliard. And we all know that Holstein, they are everywhere. So basically you can find a population of Holstein cattle everywhere. While the Nordic Red, they only exist in Nordic countries, and Montbéliard is only in France. So in order to predict genomic prediction in ProCross, no matter where you are in the world, you will need to get the purebred data from another country. So we have this problem that we need to share genotype and phenotype information between countries. But that might be difficult because those data can be sensitive. And also because we are competing on the same market, we are selling breeding material to the same farmers, basically. So yeah, you don't want to share your information with your competitors. But there might be a solution to that. So instead of sharing a data set with a large number of genomic data from your purebred population, you could instead do these summary statistics. So you basically take the summary of the estimated SNP effects and their prediction error variances, or even better, covariances. And then you technically do a meta-analysis by adding these summary statistics to the priors of the model if you have the Bayesian approach. And that is actually already done by Interpol in their SNP maze project. They are doing that for purebreds, so they are gathering summary statistics from different purebred populations and are able to predict genomic breeding values. But that's only purebreds and not crossbreds, at least not yet, maybe in the future. I'm looking at Simone and he's nodding, so. Anyway, it's very commonly done in human genetics, because in humans, they don't have large populations of genotyped individuals. So they need to do this if they want to do proper genomic prediction in disease traits, for example. And another benefit is if instead of having all these full data and only the summary statistics, you actually decrease the amount of data that you need in your model. So the aim of this study was to investigate if summary statistics can be used for multi-breed genomic prediction in crossbred animals using this BOA approach that Anna just presented, so I'm not going to tell you much more about that. So initially we wanted to do this on real animals, but because time didn't really fit into the schedule of my PhD study and the way we were using the data, we did a simulation study, and we are doing it more or less the same way as Emma presented yesterday. So just to repeat that shortly, and we also had some differences. So we simulated 3 purebred populations based on real data, genotype data from Danish animals, and those were the Danish Holstein and Danish Jersey and Swedish Red. And you might notice that the Danish Jersey is a little bit smaller breed population than the 2 others, because in the same study we also investigated the effect of having a small breed population. And I'm not gonna show you those results. I think Emma actually showed something on it yesterday, so we skip that. Yeah, so we simulated it for 12 generations, and the last generation will be our test animals, and the previous 3 generations will be our reference population. And of course, oh, wrong way. And of course, we also simulated some crossbred populations. So based on the purebred populations that we simulated, we also simulated 2 different crossbred populations, one having all 3 breeds in a rotational system, and then one having Jersey and Holstein as a 2-breed rotational crossbreeding system. And all of these animals in the 12th generation will be Holstein sired, and of course that will affect the results. Yeah, and I should also mention that the trait that we simulated was the high heritability trait, so around 0.40, so that it's more like a milk production trait. Yeah, so if we go to the results, so this is, yeah, this is just to show that multi-breed prediction works. So having so if we look here, maybe I should show. So the first row will show that the prediction accuracies for the 2 crossbred populations based on a Holstein reference population, and the prediction accuracy here is defined as the correlation between the true and estimated breeding values. And we see that the prediction accuracies in that case will be between 0.54 and 5.9. And we can see, at least for the 3-breed population, we can see a little increase if we use the mix as a reference. So having 3-breed crosses only in the reference and predicting 3-breed crosses, that's a little bit better than only having Holstein. And the same if we look at the 2-breed crosses using the 2-breed reference population. But we also see that it's actually even better if we can combine the purebreds or the crossbreds, but the best thing is to combine both crossbreds and purebreds in the same reference population. That's where we achieve the highest prediction accuracy. But the point of this study was to look at the summary statistics. So here I'm going to show that, and the first row here is actually what we saw here. So that is the situation where we have full genotype and phenotype information from both purebred populations and crossbred populations. And the second line here is the situation where we only have full genotype and phenotype from the crossbred population. So we have no information from the purebreds, and that will correspond to this row. So what happens if we have the full information from the crossbreds, but only summary statistics from purebreds? That actually increases our prediction accuracy, and we get prediction accuracies that are almost as high as having full information. At least they are much higher than having no information at all from the purebreds. So we can conclude for that it's better to have at least summary statistics instead of having no information at all. We also looked at different combinations of having summary statistics and full information. So we've assumed that you will have full information from Holstein cattle and the crossbreds, and then different situations for the Swedish Red and the Jersey. And we see that the prediction accuracies are quite high and close to the full situation. But that is, of course, because these animals are all Holstein sired. In a real situation, your crossbred animals will not be like that. They might have different sires. So we would expect that if we had for example, a Swedish Red sired, the prediction accuracy here will be lower than that. Yeah. So to conclude, we need to have these multi-breed reference populations. We need to combine all our purebreds and crossbreds. And if we can't achieve the full data, at least we should try to get the summary statistics to be able to predict. high prediction accuracies. And that was all for me.
Yes, that's lovely, Julie. Thank you. Again, have we any final questions from the floor?
Thanks for the interesting talk. So what do you do if one of your reference populations is split over several genomic evaluations? For example, the Holstein breed is computed in the US, in Europe, and all over the world. So you would have several summary statistics. Is it easy to accommodate that?
So I think here the point is that we only use it in that country you have your progress animals. But I guess in case if you use different summary statistics so you're actually doing a meta-analysis in a meta-analysis in that way. Maybe that can work, I would assume. So.
Thank you. Two short questions. First of all, is it easy to cope with different sets of SNPs in case you receive different sets from different origins? And second question, is it important to account for the covariance of estimation of the SNP effects?
So the first question, I'm not sure how to answer that, but I guess that's the best way you can do when you do the BOA approach. So that's the best way to cope with the SNP effects. I'm not sure. I don't know how to answer that, but I can answer the next question. So it's better to have the covariances instead of only the prediction error variances. And here we only had the variances and not the covariances, but they do have that in interval. So.
Brilliant. No more questions. That's lovely. Thank you very much, Julie. So that concludes our session this afternoon. I would just like to say a really big thank you to all our presenters this afternoon. We've had some really interesting and valuable work, and it's also been very well presented. And thank you for my part for keeping to time. It's made my job really easy this afternoon. So again, thank you very much.